So what we're going to be doing is changing our thinking to be able to do things, to graph things, and think about graphs or functions. They're not really functions, but equations in a polar as opposed to a rectangular way of doing things. Now, you're probably a little bit familiar with polar because our maps are done with a polar graph. Like if you look from the North Pole, right, this would be like the North Pole, and you have 360 longitudinal lines. Well, you have more than that, but if you think about when you look at a globe, you're used to these longitudinal lines going like this, right? And then you have latitudinal lines that go from 0 to 10 to 20 all the way up to the top where it's 90. Well, the longitudinal lines that come down like this, those are the lines that you see on this pole. It's almost like they took this, laid it on the top of the globe and wrapped it around. Are you kind of with me? So a polar graph is kind of gridded like that. So what you might call the x-axis, all right, if you might call it the x-axis, we don't have an x-axis anymore. There is no x and y, but if I were to lay it over this, the x-axis would be like at 0 degrees. Okay. Now, again, there is not an x-axis. So you can draw a big line like this if you want. And sometimes you might see that on your calculator because your calculator sadly doesn't have a really nice polar grid. It can graph things, but it just doesn't have a pretty polar grid like this. I pulled this off something else. And I do have some lovely graphs with some polar curves that I've put together in this giant file that I use for tests and worksheets and junk like that. But sadly, your calculator will still have an x and y axis, even though it will be thinking in r's and thetas. So so this is what they call the polar axis. If you want to write that down somewhere, I don't even know that I asked that, but the x-axis is like the polar axis. The origin is the pole, P-O-L-E, okay? And then from that, it just goes along. 1 degree, 2 degree, 3 degree. I've marked off 15, 30, 45, 60, 75, 90, because that's, not just the 30, 60, 90s and the 45, 90, 135s. I put an extra 15 in there. But anyway, this is how we would think. Instead of going like we would with a point, like in a rectangular system, like in an XY, if I was going over 3, up 4, over 3 from here would be 1, 2, 3, right? And then you would go up whatever 1, 2, 3, 4 would look like. So it would look something like right here. Okay? So if this was a big X and Y, I would have gone over 3, up 4. Are you with me? But I don't think that way on a polar graph. On a polar graph, I'm thinking r theta. And r is like a radius, a distance away from the pole. And then theta would be the degrees that I moved. Okay? So in a situation like this, if the 0.34, if I needed to convert it, instead of marking off 3, 4, which I don't have that grid here, I would need to know, well, how far away is this thing from the pole? And I need to know what degree angle I'm going to be moving before I start heading in that amount. This would be how I think. I would need to know that theta right there to be able to go, all right, I'm going to head over theta, and then I'm going to march out 1, 2, 3, 4, 5 to get there. And I know I'm marching out 5 because you can kind of tell if I was over 3, up 4, that would be 5, right? So the question would be, what is my r and theta? And how would I find that so that I would have it in what we call polar form as opposed to rectangular form? Okay? And if you really think about it, it makes sense. Like, I mean, if I really wanted to get over there and chat with Maddie, am I going to go, walk over there on the x-axis and then turn and walk over here on the y-axis? It really makes a lot more sense to point a certain degrees, right, and walk straight there. Now, if I need to get in the back, I guess going rectangular might make sense, but truly, this probably makes a lot more sense, but it's not how we typically deal with functions. When we deal with functions, we're talking about plugging in x's and getting y's, and all of that thinking is done on an xy plane. So we're not going to necessarily, these aren't necessarily going to be functions, they're going to be graphs, but I can graph circles, lines, all kinds of weird shapes like lemniscates and cardioids and limacons with inner loops and all kinds of different things that we will look at starting tomorrow, the next day, or whatever, that are in polar form. But again, there's no more X's and Y's. It's R's and thetas. So how do you make this conversion? Well, I think if you saw where we got this point right here that was the radius was 5, you saw that connection, right? If you have an X value that's 3 and a Y value that's 4, kind of makes sense that the R value is going to be found through the Pythagorean theorem, right? So my R value is basically just my X squared plus my Y squared. And when I square root it, that gives me my R value, right? So really clearly, if I have 3, 4 here, my R value can be found by squaring the 3, squaring the 4, adding them together, square rooting. Great, so I have my R value. Now, how am I going to find my angle?
You just find it.
How? Now, I can use sine and cosine now that I have the number 5, but what if I found 5 wrongly? Like, what if I accidentally made a mistake? Then I would be using that wrong mistake. Is there a trig function that uses X's and Y's? Tangent. So I'm going to use tangent to find the angle. And that makes sense, right? The tangent of the angle is Y over X. And every point is giving me a Y and an X, right? So for me to find the angle, I'm just going to do the inverse tangent of the Y value, right? In this case, the Y value is 4 over the X value. So in this particular case, I've got inverse tangent of 4 over 3, and I type that in my calculator. Is there any time, by the way, where my calculator would lie to me?
The y is negative. The x is negative.
Talk more.
Isn't it if the pi is negative?
Do what?
If it's in the place where like tangent's negative.
No, but you're thinking right. If it's in
negative.
Okay, so if it's in a quadrant where inverse tan is not defined, where is inverse tan defined? Between 90 and negative 90, not including 90 and negative 90, right? Because it's undefined there, but anywhere from negative 90 to 90, so there to there, not 300, not 330, but negative 90 to 90, I'm okay. So bottom line, if your point was in the second or third quadrant, then clearly the angle is not going to be negative 90 to 90, and your calculator is going to lie to you. So when it does lie to you, how do you fix it? You add 180. Because what will happen, like for instance, let's just say I was at the point negative 3, negative 4. If I plug negative 3, negative 4 in there, right, the negatives are going to cancel. So my calculator is going to think that it's an inverse tan of a positive value, and it's going to throw up an answer in the first quadrant. But you know it's in the third quadrant. So, but you can see that they are 180 degrees apart. So in this case, it doesn't matter. What's a quick way of looking at that point and seeing if it's not in the first or fourth?
The x is negative.
If the x is negative, you're moving left. So if you see a negative x, just get it in your head, oh yeah, for the angle, I got to add a 180. Now, I like to leave my calculator in degrees because I would rather see an answer like, and I'm going to do this right here, I would rather see an answer like 53.1 than 0.927 radians. 0.927 radians probably doesn't mean a lot to you. I mean, does it? You're like, oh yeah, 0.927 radians. Sweet. Like that doesn't mean much to me. But if somebody says 53 degrees, I immediately have that mental image of about right here. So I'm going to do all my answers in degrees. And sure enough, right here, I get 53.1 degrees if you're rounding. So my 3, 4 in rectangular form converts to 53.1 degrees in a polar form. So I would just go right here, go to 53.5, and you can see if that's 45 and that's 60, halfway is about what? 52-ish. And you can see this was just a little bit more than halfway, 53-ish. So even my sketch was fairly accurate, right? But about what I basically do is head towards 53 and then march 1, 2, 3, 4, 5 units. So really, we're not doing any of this if I was graphing it. If I'm graphing this, I am literally just saying, if I had this, I would go, all right, 53 is about right there. So I'm going to go 53 degrees, 1, 2, 3, 4, 5, mark the point. That's how a polar coordinate thinks. Are you with me? So the conversion is always to find the R value. You take the square root of the sum of the squares of x and y, and to find the angle, you're going to inverse tangent with y over x. That's just using your tangent rule. But don't forget to add 180 if my point was in the second or the third quadrants. Are y'all with me? Okay, what if I'm going the other way? What if I know the polar form and I want rectangular? So what if I told you, all right, we've got the point 3, 125 degrees. So you know 125 is somewhere right in here. And I want to go 1, 2, 3. So I want something like that point right there. Something right there. But how would I find that rectangular coordinate if I know R and I know theta? Well, now what do I need? X and Y. Okay, one at a time. What do you know that would link X, R, and theta together? Cosine. Cosine is defined as X over R. So if I want X, all I have to do is say R cosine theta. What links Y, R, and theta together? Sine. If I want sine of an angle, all I have to do is go R sine of theta. So really, and here's the beautiful part, you don't even have to think about the angle. Because if the angle is in the second quadrant, cosine values will be negative, sine values will still be positive. If it's in the third quadrant, cosine values will be negative, sine values will be negative as well. It will figure out the signs for you, and you don't even have to think about it, right? So in this case, all I would have to do to figure out my X and my Y, I just memorized this, but if I ever forget, remember, it just comes from a cosine curve. Right here, all I got to do is say X is the R value 3 times the cosine of 125, and Y is the R value times the sine of 125. And typing those in my calculator, yes, I'm going to get a decimal. But I get what? 3 cosine 125, 3 sine 125. So I get, I'm just going to round, negative 1.72, positive 2.46 if I'm rounding. So negative 1.72 and 2.46. Negative 1.7 is about here, up about 2.5. Well, if that's about 2.5 if I was eyeballing it. Yeah, so pretty accurate. Notice I'm using the X and Y axis to graph them, right? Even though there's not one there, I'm just kind of pretending like this is my X, pretending like this is my Y, and kind of thinking in terms of that. Are y'all with me? Yes? Okay, there's more than one way to think about this too. Also, I mean, there's more than one way to write points. Okay, so I'm going to see if you can think a little bit. Getting rid of all this. I'll leave that there for now. All right, what if I gave you the point 4, 150? So where would you go to graph 4, 150? So you'd look at 150, which is right here, and you'd go out 1, 2, 3, 4, right? Okay, what if I instead said negative 4, 330? What do you think that means? Said that's a good guess. You look at 330, but instead of walking 4 that way, you walk 4 the other way. So if I look at 330, but instead of going 4 that way, I go 4 back the other way, these turn out that they're equivalent. All right? What if I said, what about -4, -30? What is that telling you to do? Go down to -30, which would be 330, and again, go back 4, right? So when you look at these values, what does it look like I'm doing from here? Adding 180 and changing the sign, or subtracting 180 and changing the sign? Is there any other thing that I could do? Adding 360. And isn't adding 360, if you think about it, that would give me what, 510? Isn't adding 360 the same thing as adding 180 and changing a sign, and then adding another 180 and changing the sign again? So the bottom line is there are all kinds of different, there's an infinite number of points of ways I can label that point. And all I got to do is take what I think it is by just looking at r and theta, and then just add 180, change the sign, add 180, change the sign. And I could do that all day long if I really wanted to. Y'all with me? Okay.
Or we have a question where we have to give like all the different answers.
Well, there's an infinite number of them, but there might be something like, hey, what's the same, pick the point that's the same as this. And I might have a bunch of stuff, and all of these would work, but I could have other ones that kind of look like they might work, but they really don't, right? Like that's not the same, because that's saying 330, 1, 2, 3, 4 that way, right? That's not the same thing as that. But anyway, all these other ones are the same thing. Y'all seeing this? Okay, trying to make sure I don't forget stuff. Okay, so that is converting from rectangular to polar and vice versa. Now I want to talk about what do you do with equations? Okay, so we know we already have functions or equations, whether they're functions or not. A circle's not a function, but I can still write it with x's and y's, right? Well, what if I wanted to convert something in rectangular form, but not a point, an equation, and I wanted to convert it out of the x's and y's that rectangular form uses into r's and thetas, which is what polar form uses. So I'll start with something kind of basic. So what if I started with something like x squared plus y squared equals 9? Now, again, rectangular form uses x's and y's. Polar form uses r's and thetas. What could you do to change this into polar? Now, if you think about it, you already have a bunch of links. We already said that x was what? Hey, why am I using this? Hold on, I don't need this anymore. Well, I'll tell you what, I'll leave it up for a second. We've already said that r equals what? X cosine. I'm sorry. No, we didn't say that. We already said that x equals what? R cosine theta. We already said that y equals r sine theta. So if I wanted to, I could make 2 quick substitutions in there. That's not the best way, but you could. I also already said what? X squared plus y squared equals r squared. That makes me think, oh, that would be a lovely substitution, right? What else have we already said? We said that tangent of theta was y over x, right? And we've also solved. We've solved for r here, and we've solved for theta there. So we've done all these things. Well, when I look up here, if I want this equation to no longer have x's and y's, but now to have just r's and thetas, and by the way, you don't have to have both. There are equations here that just have x's, right? X equals 2, y equals 3. So you might just have an r or just have a theta, but most of the time you have both, just like most equations have both, x's and y's. So what do you see you could do right here? So I could replace that with r squared. Now that doesn't happen very often. It happens with circles though, right? And if I replace that with r squared, what are you left with?
R equals 3.
R squared equals 9, which is the same thing as r equals 3. Now, if you really think about it, what does it mean if they don't mention anything about the angle? Which means the angle, I guess, could be anything, but the r is always 3. Well, think about it. If this is polar, I'm saying the r is always 3. Doesn't matter what the angle is, but the r is always 3. What do you end up with? A circle. And sure enough, that is a circle. R is 3. And if I thought about it like this, if you're like, wait a minute, technically it's not r, it's r equals plus or minus 3. Okay. So instead of going out 3, I'm going to go back 3, back 3, back 3. It's still the same points, right? Are y'all seeing that? Now, what if it wasn't a circle? Like, what if it wasn't x squared plus y squared? Well, in that case, what could I do? Like, what if you didn't see this part? Couldn't you just replace, and this is usually what you do, replace any x with that and replace any y with this? If I did that, what do I get here? So I would get r cosine theta squared. I'm going to not go as far as you did on the first. And then when I replace the y, I get r sine of theta squared. Now, isn't that r squared cosine squared and r squared sine squared? And what would happen if I factored out an r squared? That is all a big Pythagorean identity, isn't it? So there I'm back to where I was before. So there are a lot of cases where you have a polar graph, and by the way, we don't do that a ton. I mean, most of the time we have polar graphs, and if we don't know what they look like, we change them to rectangular form because we're accustomed to rectangular form. Kind of like maybe in 7th grade when you had a base 7 number and you're like, I don't even know what that is. But if you change it to a base 10 number, all of a sudden you're like, oh, I know what base 10 is, right? We think in base 10. Well, we tend to think in x's and y's, not as much in r's and thetas. So if I were to give you something like r equals 3, yeah, it kind of makes sense that that's a circle. But what if I said theta equals 30 degrees? What does that mean? What does it mean if I say r equals 3 cosine theta? What does that mean? So we're going to learn about the nature of some of these graphs and what they look like. So when we look at them, we go, oh, that's a blank or that's a blank. We need to know that. But sometimes we're like, I have no idea. So I will replace some stuff, change it to here. But you can go from rectangular to polar. You'll probably be asked to do that once. But the bottom line is just replace x with that and y with that, and you're done. Yes?
Ever have to know how to do the base 7, base 8 kind of stuff? Done with it.
At a math tournament, you might not want to know. I mean, you might need to. I don't see it very much anymore on the state tests. It used to be all over there, and they were really tricky stuff. Do what?
I never learned how to do that.
We can talk about it on the day. If it shows up, we'll certainly talk about it. I'm on any of the tests that we're doing, but not today. All right, so anytime you have rectangular, if you need to go to polar, you just replace x's with that, y's with that. Now, do you simplify? On your calculator, there is a mode. Like if you go to your Inspire, if you have it in front of you, you can do this right now. We're going to do a lot of this tomorrow. So if you're on your calculator and you go to the graph, like you're going to graph something, okay, you can delete all that junk out if you want. So if you're, and you can change your window to standard. Okay, so I'm on a standard little X and Y plane. Well, you're in function mode. You can tell that because if you go to menu, graph entry, like how do you want to enter the graph? If you hit 3, at the very top, you see function. The next one down, usually you see relation. Relation allows you to graph circles and ellipses because it's in a different form. Those aren't functions. But look on down to number 4, 5, or 6. What do you see? Polar. And if I click, mine's 5. If I hit 5 for polar, what pops up? R and theta. So what pops up is not, actually just R of theta pops up, not R and theta. So R of theta pops up, which means it's like a function mode, the R of theta. But basically what you're doing is you're going to graph a function in terms of whatever. So like right here, I would have to solve for R, and I would go, well, R of theta is 3. So if you want to, you can hit the number 3 in there and hit enter, and what do you see? There's your circle. Now, for the record, it will only graph it based on the number of degrees you want it to graph. What do you have? Are you in radians? Hold on, mode. Go to radians. Put it in radians and do it. Okay. You can do it in degrees, but it might be better to keep it. I don't know what's better. If you change it to degrees,
No, it's not. My window's open.
actually, I don't know why. Anyway, whatever. Are y'all with me on that? Now, watch what happens if I go back to, if you hit tab and go up back to R1, do you see the step right there? Now, if you're in degrees, that's fine. You want to be in degree mode, but you have to change your step from 0 to 360. If you're from 0 to 6.28, it thinks, and you're in degree mode, it thinks, oh, I'm going to graph the first 6.28 degrees, which is not much, right? It's going to go whoop, and give you just this little section right there. I need all 360. So you can see if I were to go down and change my radians from 6.28 to 3.14 and hit enter, what do I end up seeing? A semicircle, because it's graphing like this. 1 degree, 2 degree, 3 degree, 4. It's literally going through 180 degrees if that's all you have, and it only gets half the circle in. So you need to go at least 1 revolution. Some graphs take more than that. Some graphs take 10 revolutions to get it in. I mean, it just depends on your graph. Are y'all with me on that? And the little step that you see, the step means how accurate do you want me to be? And when it talks about how accurate, this is how this calculator thinks. Literally, it will start like this when it's graphing. It'll plug in, like if your step, right, my step is 0.13. So every 0.1 radian, it marks a point and connects them. So it's starting at 0. It has that point. And then it goes 0.1 radians and then connects. 0.1 radians, connects. 0.1 radians, connects. 0.1 radians. Well, look what happens if I change that step to 0.5. What do you see? Actually, not much change. Let me do one that's a little better. What happens if you change that step? Oh, it won't let me change it. Hold on. Yeah, it did. I'm going to go back to 6.28. And I'm going to change my step to 1. A 1.0. And look at, you can't. Why is it doing it so well? It shouldn't be doing it this well.
Put it
2.0
10.
2.0 looks kind of weird.
Okay,
Put 10.
Guys, if we just keep saying stuff, I'm sure.
Oh, if you put 10, it puts a little triangle thing.
yeah, well, bottom line is, the bigger the step, the more space it goes till it marks a point, and then it connects the dots and it puts a flat side in there. Right? So the bigger your step is, like if you put a step of 10 in there, it's going to go a whole bunch and it's going to go bloop, and you're going to see it and like, that's not a circle, but you know it's supposed to be. So if you keep the step at like 0.1, or if you're in degrees and you change your theta from 0 to 360, make your step like 5 degrees. Just make sure you have a bunch of steps so it marks a bunch of points and gives you a decent looking curve. All right? Because if you make a really big step, it's going to skip to that thing, put a straight line. Skip, put a straight line. And that's normally not a good idea. You end up with like a hexagon or a pentagon or a duodecagon or some other weird thing you learned in Elmer's class. Okay? Are you with me so far? We'll talk more about the calculator later. Now, what if I gave you something like this? What if I had a rectangular graph that looked like x equal 4? Well, we know that x equal 4 looks like what? Vertical line right here, right? So if I want to change it to polar, tell me what you have to do. Replace x with r cosine theta. And if I wanted to graph it on my calculator, I have to solve for r. So I'd have to divide by a cosine. And if I wanted to, I could rewrite that as a secant. And I could graph this. So my polar graph would be 4 secant theta. Right? And when theta is 0, secant of theta is 1. 1 times 4 is 4. So at 0 degrees, we are going to be out here at 1, 2, 3, 4. And then if I plug in 15 degrees, I get a value that's a little bit more than 1. You can try it, secant of 15 degrees. If it's in degree mode, you get a little bit more than 1. And you multiply by 4, and it gets actually out here a little bit further out. And if you plug in 30 degrees, it gives you a little bit more than that, and you multiply by 4, and you get a value that's like right here. And when you plug in 45 degrees, you get a value even more than that, and you multiply by 4, and you get a value up here. And as you do this, you'll see that all of these points right here end up lining up on a vertical line that looks just like x equals 4. But who cares? All the question is going to be is, what is this? This is in rectangular form. Rewrite it in polar form. Okay? Now, most of the questions you will see are situations where I give you polar form and ask you to go back. So there are some guidelines I want to give you on doing this. So if I, come on. Really? Ha. You lose. So let me just talk about these guidelines right here. And you ought to write these down because I kind of do them in my head. But anyway, first rule, okay? Your first rule is to, no matter what you see, we do not deal with cotangent, secant, or cosecant. If you try to manipulate these rules while using those, you're bound to get yourself into trouble or to get an equation that has really higher powers that gives you extra answers, and you won't have a clean, precise answer. So first thing, get rid of cotangent of an angle, secant of an angle, and cosecant. Now, what do you think I mean by get rid of them?
Changes the sign.
Yeah, I don't mean like take them and throw them in the garbage. I mean do the reciprocal so that they turn into tangents, cosines, and sines.
Gently write them.
Do what?
Then gently write them.
Yeah, no garbage. Okay, second thing. The second you see a fraction, eliminate it. Eliminate fractions immediately. So what I mean by that is if your initial equation was a fraction, cross multiply, and now it's not. The second you replace cotangent with 1 over tangent, it's a fraction, multiply through by tangent, so it's not. You're always getting rid of fractions immediately because you don't want, sometimes having them in there, it just messes you up. These rules I have discovered always get you where you want to go nice and neatly. Third thing, then if you see an R after doing this, replace R's with the square root of x squared plus y squared because that's what it's equal, right? Or, if possible, replace R's with, replace, hold on. Or if you happen to see an R cosine theta, you can replace it with an X, or a R sine theta, you can replace it with a Y. So I'm going to put that in parentheses, but here's the great thing. If I did have an R and a cosine theta, okay, if I did, what's cosine theta? What is cosine of an angle equal to? X over R. So if I replace cosine with X over R, what do I end up with? X. So that works out greatly also. And remember, if I am in, this is to go from polar mode to rectangular. All right. So if I want to go from polar to rectangular, these are the steps that you're going to be dealing with. And notice, if I have an R cosine theta, immediately my R's and thetas are gone and I have an X. If I have an R sine theta, immediately I go just to an X. If I have just an R by itself with nothing else, I immediately have gone to a rectangular situation. So these are all wins for us in dealing with R. And then fourthly, replace theta. What are thetas equal to? How have you been finding theta? The inverse of tan. The inverse tan of y over x. So if you see a theta, replace it with inverse tan of y over x. But If you see a tangent of theta, just replace it with y over x. Either way, you're getting to just y's and just x's from your theta, which is a win because you're trying to go to rectangular form. So from here on out, I'm just going to give you examples and show you what we're doing. Now, again, we're getting 2 x's and y's. So when you look down, you know you're finished when you don't see any more x's, any more r's and thetas. If there's still an r or still a theta, you're not done. And if you don't follow these rules in order, you're going to run into trouble. I can promise you. It happens every year on the test. I can just tell what people didn't do. Does everybody have that? All right, I'm going to a new page. It's still there if we can come back to it. So first example, I am changing on all of these from polar to rectangular. So your first one, r equals 3. So I need to get rid of r. What is r equal to? The square root of x squared plus y squared equals 3. Are your r's and thetas gone? Yes. So technically you have made your conversion. Now I will say this. On a lot of the homework problems and on my test, I will say put your answer in ax squared plus by squared plus cx plus dy plus e equals 0 form. Now that doesn't mean I always have an x squared and a y squared, but you're going to have that a lot. So is that in that form? No. But if I squared both sides, is it in that form now? No, but pretty close. X squared plus y squared minus 9. Look, x squared, y squared is constant. X squared, y squared is constant equals 0. Okay, I'm good. So far, so good? All right, here's number 2. That first one was example 1. Theta equals pi over 6. Now, you'll notice I didn't use a degree. You want to change it to 30 degrees. It really won't matter because you're getting rid of your r's and thetas anyway. You're going to have nothing left but x's. So if you want to think in degrees, make it 30 degrees. So what do I need to do to get rid of a theta? Theta is, I've been finding theta by doing the inverse tan of y's over x's. Okay, now, do I have any thetas and r's left? No. So that's a win. I am technically in rectangular form. I'm just not in a pretty rectangular form. So what can I do at this point to get rid of that inverse tan? Tangent both sides. So a tangent on the left gets rid of that. And a tangent on the right. Oh, wait, I know the unit circle. What is the tangent at 30 degrees? Root 3 over 3. So y over x is root 3 over 3. And at this point, what could I do? Cross multiply. So 3y equals root 3x. And what can I do now to get it in that form? Okay, so if I subtract 3y, I would get root 3x minus 3y. And technically, that's 0 equals root 3x, root 3y. That's fine. You don't have to have the 0 on the right side. But so that would be a good form. By the way, there are other ways to write this answer. I mean, there's other ways. Like I could have written it as 0 equals 3x minus 3 root 3y. I mean, it might look a little differently, but that's okay. All right, what if I gave you this? Again, same directions. Example 3. R equals, see if you can remember your rules, cosecant theta. What's going on? We don't deal with cosecants, cotangents, and secants. So what is cosecant of theta? 1 over sine theta. We don't deal with fractions. Multiply both sides by a sine. Now, I still have r's and thetas, but at least I've gotten out of those 2 emergency modes. Any ideas? Oh, r sine theta is y. Great. If you don't remember that, but you don't want to put an x squared plus y squared in there because it just creates a bigger mess. Okay? Like, look what would happen if I put, for r, if I put the square root of x squared plus y squared. Then you're like, well, crap, what do I do to get rid of sine of theta? And then you might think, oh, okay, I guess I could change sine of theta to y over r. Oh, look, I have another r. So I guess I could go x squared plus y squared times y over the square root of x squared plus y squared. oh, they have fractions that cancels, and I end up with y equals 1. What would have been a whole lot easier? R sine theta is y. Y is 1. So it turns out R equals cosecant theta was just a horizontal line in a different mode, different process. Are y'all with me on that? So if you really know your stuff, you can avoid this kind of thinking. But anyway, moving on. What about this? R equals, that feels so, well, 4 sine of theta. Any ideas? Now, for those of you that are like, well, I could change R to the square root of x squared plus y squared, but I could, and I could get down that road. It would kind of feel like this.
And you just said 4y.
Well, hold on. Y is R sine theta. I don't have an R.
Could you change it to x over sine theta?
I could change sine theta to y over r, which puts another r in there, but I got a fraction, so what do I do immediately? Multiply through by y. Look how this helped me. By just using my trig function, now I have an r squared, and what's an r squared? Just an x squared plus y squared. And now what do I do to get it in that right form? Anybody recognize what this is? That's a circle. Anytime I have x squareds and y squareds with the same coefficient and the same sign, as long as it's not degenerate, which it won't be when you complete the square there with the y's, you get a circle. So this is a circle with the shift over there at +2 with a radius that ends up being of a +2. But you would see that if you completed the square, which I don't need to on this film. All right, what about this one? This is probably the trickiest of all of them. Maybe. Yes.
Fraction.
Fraction, got to get rid of it. Cross multiply 2 times r minus 3r sine theta equals 6. Is everybody with me on that?
Change the negative 3r sine theta to negative 3y.
Okay. R sine theta is y, or sine of theta is y over r, and the r's cancel. Doesn't matter. Now remember, you have to have an r. Don't look at the 3 and go, I thought the 3 was the r. If it's the letter r with the sine of theta, you can use y. If it's the letter r with the cosine of theta, you can use x. But in this case, if you replace sine with y over r, you'd still end up with a y because the r's would cancel. But anyway, you are correct. R sine theta is y. Now I am to here. What am I still having this problem that's bothering me?
R.
So I really have no choice but to replace that r with a what?
The square root of
A square root. Now, does that look like the form I am seeking? I got to have ax squared plus b. So what am I going to have to do to get rid of that square root? Do I square it right now?
No.
Because that would give me a binomial squared, and I would have a middle term that still has the radical. So I isolate it. And this is probably the hardest one because you have to square both sides. Squaring the left side gives me a 4 out front, but the radical goes away. Squaring the right side, be careful. Square the first. That times 2. Square the last. And then to get it all on one side, what do? I got to distribute that together. So I get 4x squared. Now I do get 4y squared, but when I subtract the 9y, I get what? Negative 5y squared. When I subtract the 36y, negative 36y, negative 36, all equal to 0. And tell me, when you look at that, what do you see? Hyperbola. That's a hyperbola. All right, see what you can do tonight. And good luck to you.
Yeah, Kayla's logos are a lot more than
See ya. Have a good one. Yeah.
Yesterday, my softball coach told us we have a tournament on the 26th. And so I told her that we had that tournament, and she was like, "Can you just talk to him and see if you can figure it out?" And
When's your tournament start and where is it?
I think it's in Pelham, and it will start depending on how we do Friday.
Would you be playing before 10?
Possibly, if we're like losing or something on Friday.
We can play it by ear.
Okay.
I mean, I've already paid for you.
Okay.
So we'll probably have a little option where you can test from 7:30 to 9:30. Most people are going to test 9 to 11.
Mhm.
But so if you had like a 10 o'clock game, you'd be running close. But maybe you could get a quick warm up. Pelham's not far from here,
Yeah.
so you could get there in probably 25 minutes on a Saturday morning, easy.
I could just tell her we only have one tournament.
Well, tell her that for sure. But you a starter on that team?
Yeah.
What do you play?
Oh, anywhere.
Anyway,
Yeah.
yeah. Well, we'll figure it out. I mean, don't worry about it. If it's something where it's critical that you be there, we can let you go. But I would love for you to be here. And since we don't even know, let's just wait and see
Okay.
what happens.
Thank you.
Yeah. I'll probably forget this conversation in about a month. So yeah, remind me.
I will.